Bismillah ar-Rahman ar-Rahim. Ladies and gentlemen, welcome to the online workshop on machine learning. And this is level 3. I am Dr. Saleha Naghmi Habibullah. I'm a professor of statistics at Connect College for Women in Lahore, Pakistan. And also I'm honorary director of the Pak Institute of Statistical Training and Research, that is PISTAR, right here in Lahore, Pakistan. The focal person for this workshop is Dr. Syed Wasim Abbas, who's Assistant Director at the Bureau of Statistics, Punjab, right here in Lahore. The plan of today's workshop is as follows. I will be introducing, I will be requesting Dr. Sharka, my dear colleague, to introduce Associate Professor Dr. Aisha Bilgin. And after that, Aisha will be presenting her keynote address. Some of you will recall that she was doing so last time, and such excellent address she gave. But due to shortage of time, I had to request her to present to us the second example that she was going to present in today's workshop. And she has been extremely kind that she has once again created time for us and will be presenting that example and whatever else she wants to present. And that will be happening today in the beginning of the workshop. I would like to encourage all of you to put forth questions to her, because, you know, it is always better, understanding enhances if there is a question answer session. So I have allocated about 10 minutes for that. Of course, all these timings are approximate. Try to make a good estimate of the time that would be required for each one of these items that you see here. After that, we will be having the workshop by Dr. Reza Arabi Belaghi and Dr. Alireza Safariyan, both of them from Iran, our dear colleagues from Iran, and our neighboring country, and also sharing the same religion, Islam, Deen Islam. After that, we have the commencement of the short break. Now, you know, the short break is quite short. Usually I say 7 minutes. This time I have written like 8 minutes. And in that short break, for the Pakistani participants, I would like to introduce the ISLP and International Poster Competition. And me and Dr. Sharka Hashmi, who is the focal person for this competition, we will be talking to you about this. And we will be encouraging you to, to get hold of some of your students, all those who are in, teaching, and register very quickly within the next 4 days, because according to the ISLP, which is the International Statistical Literacy Project, the deadline for registration is 15th of January. I have sent hundreds of emails all over Pakistan, and we have got responses. We would like to have some more, because this would be the first time that Pakistan would be participating in this competition, which has been running for about 28 or 30 years, the ISLP project. And this competition, I don't know exactly how many years. Aisha might be able to help me. But anyway, we will be talking about it during the short break. And after that, we will resume the workshop on machine learning, which will hopefully go up to 4:35 p.m. approximately, after which again we have a question answer session slot. And again, I would like you people to put forth questions. Please do not be shy. Do put forth questions at that time, so that if there are some confusions, something for example, I could not understand, I would like to ask. So please do make use of that. After that, I have put some time for feedback from participants. This depends on whether we are able to stick to the timings that are written here. If there is time, then please do provide some overall feedback, not only on this series of workshops on machine learning, but overall on this all these initiatives that are being taken by PISTAR. Just before I forget, I would like you to know that we did in one workshop have about 10 minutes for this informal discussion or feedback. And I talked about one other initiative that PISTAR could take, and that was statistical consultancy. And one of the participants who's right here today also, she said that, yes, I'm interested. And I would like to give you the great big news, the good news that we have started this initiative and the consultancy sessions have actually commenced. So this is another dimension. And after that, we have the vote of thanks to be given by Ms. Kamal Aslam, my dear student and member of the PISTAR team. And after that, the closing. Thank you very much. So these are the participants from Pakistan. These also are my dear colleagues from Pakistan. There are more colleagues, mashallah, from Pakistan. And then we have all these international participants, our dear colleagues from Saudi Arabia, Canada, Turkey, Denmark, and Kenya. All right, now I would like to request Dr. Sharka Hashmi to introduce to you Associate Professor Aisha Bilgin.
Assalamu alaikum to everyone. Associate Professor I.C. Bilgin, President-elect IASE, Department of Mathematics and Statistics, Macquarie University, Australia. Associate Professor I.C. Bilgin is active in the statistical analysis and the design of studies in health and statistics education. Her research in health developed to include adolescent health and recently studies related to breast cancer, MS, and Alzheimer's disease. She is one of the pioneers on applying machine learning to health datasets. Recently, she was awarded Excellence in Research, 5 Future Shaping Priorities, Healthy People by Macquarie University. IC has won several learning and teaching awards for her outstanding contributions to student learning, such as ALTC citation for outstanding contributions to student learning. Her pedagogical research interests are focused on statistics education, such as learning approaches in statistics, impact of learning spaces to students' learning. She is president-elect of the International Association for Statistical Education, IASE. So the title of the talk is Machine Learning Application for Health Problems. Thank you.
Thank you so much, Dr. Sharka. So Aisha, would you like to share your own screen now?
Yes, I'll do that.
Okay, so I will stop sharing mine. Thank you.
Let me just find it. Okay. Can you see that?
Yes. Please go ahead.
Good. Okay. So roughly a month ago, we talked about one application of classification techniques to predicting depression for young people. I have 2 other case studies. Hopefully I'll remain within my time frame, and I'd like to have some concluding comments. Let me just have a look at my time. Okay, so this case study is related to multiple sclerosis from an institution in my university. They've been working with application of understanding whether kynurenine pathway makes a difference to certain diseases. So 2 of the studies that I'm going to present, both multiple sclerosis and the breast cancer, it's basically looking at kynurenine pathways where they're using the chemicals in this pathway, we will be able to predict either different multiple sclerosis or different breast cancer types. So what we've done is, I mean, it was important to be able to do this research because what they were thinking that maybe this multiple sclerosis is an important disease. They did know that, but it's not possible to understand why some of the patients were progressing to the secondary MS, which is not reversible and really dangerous, and 50% were remaining RMS, which are functional, but when they progress to the higher levels of MS, they became infunctional and they need more help. So they needed to understand whether some of the chemicals in that kynurenine pathway would make a difference, and if so, informing doctors about that will help them to predict who will be more likely to progress, and then they could maybe prevent it or delay the progression from one level of multiple sclerosis to other one. So it was important. It was not life-saving, but it was deferring the progression of the disease. In this one, it was quite a comprehensive study. Some parts included normal statistical analysis, looking at longitudinal change. Some part was just looking at different kinds of multiple sclerosis. And we also had a test cohort. So it took us to complete this study more than a year. Not the analysis, but more so the analysis in the lab. So they had to do their chemical analysis to be able to identify what was what. And then we had to work with that. And they also had the healthy cohort. So that was actually good to have. So cohort 1, what we had there is 136 patients. I mean, what you are thinking when you think about the machine learning, it's applicable to big, large data sets, but it is also applicable to small data sets like we see here. So one of the things that why we have used machine learning instead of standard statistical analysis, it's because the predictors are highly correlated with each other. So it's hard to do a full comprehensive statistical analysis when the predictors are correlated with each other. But applying the machine learning techniques, we can do that. And we are able to also find in normal statistical terms interactions, while the main factors might not be significant. So it's actually good to be able to do that. So you can see the distribution of different cohorts with different number of patients. In cohort 3, you think it's only 10, why bother? The reason for that, they were comparing samples from, they were comparing samples from fluid taken from the spine versus the normal blood test results. That's why they only had 10 patients there. I have used IBM SPSS modeler to do the data mining techniques, machine learning techniques, as well as R packages for pre-processing the data and visually displaying the data. I haven't done my machine learning algorithms in R, which I could have, but I haven't done that. The classification and regression things that I have used, or machine learning techniques that I have used, include decision tree. And when I have modeled training data, which was my cohort 1, I identified the C5 decision tree was the best model to be able to differentiate between the MS subtypes. So therefore, I have used the results from that model, where I was able to identify the most important variables based on the impurity measures. And these are the chemicals. Some of them it's I mean, for us, it doesn't make much sense because we don't know what they are, but my chemical scientists and health scientists, so for them, it had quite a lot of importance to be able to identify these things. And also, the results are published in a journal, which will be mainly talking to the doctors. So for the doctors, it makes sense to understand what they should be looking for to be able to identify which category of multiple sclerosis the patients could be. So we, out of so many predictors, we identify these variables as the most important variables to be able to predict which category of the multiple sclerosis the patients could be. We've also displayed our C5 decision tree. You can see the color coding there. And this is my root total number of observations, which includes the healthy cohorts and 3 different kinds of multiple sclerosis. And what happens with multiple sclerosis, RRMS progresses to SPMS, whereas PPMS, it's just occurs. It's not a progression, it's not the last step or anything. It occurs itself and there is no going back. What they wanted to know is the RMS patients progressing, the main difference between these 2 cohorts, basically. So if they could identify those, the chemical wise, they were able to do something with the RMS patients to be able to defer the progressions for the SPMS. So that was the idea. And this TNF alpha, as I said, these are have some meaning in the body, apparently, and this kind of analysis were never done before. So for them, it was really important to be able to see which chemicals are important. And you can see here picolinic acid. And if this is less than certain value in that PPMS group, you can see there's some little other type, but mostly they are PPMS patients. And when the things are shown as not splitting again, these are the leaves of the tree, whereas that one is the branch of my tree. So we have calculated and sensitivity and specificity, including the healthy cohorts. As you can see, they are very high. So it was really good. No, usually you overfit to the training data, whatever you do. I have done some cross-validation, tenfold cross-validation to decrease it, but we also wanted to really predict what is happening in different categories of MS. So therefore, we have also used that training model created using the training data in the test data. You can see that sensitivity specificity went down slightly, but still it's quite good compared to what they were able to do in the past. So we took it from there. And what we have done here is we can say that 6 predictors identified with that model is able to predict which MS subtype the patients will end up based on these biomarkers. So for them, it was really good to be able to do that. We have developed the model in the training data using different models and identified the best model. And we presented the results for best model in the training and also for the test. Normally in the computer literature, they only present the result for the test. I don't like it very much when they do it that way because you don't know how stable the model is if you only look at the result in one data set. When you look at the result for the training and the test at the same time, you can actually see how stable the model is. There is no guarantee if I had another test data set, the results will be exactly the same. I mean, nothing is exactly the same. You know that the samples vary from sample to sample, but at least we are able to see how much the results are changing from training data and test data. So I would strongly suggest you, if you are presenting your results, do present your results for test data and the training data to give an indication for the final users how stable the model is from different data sets. Final case study is about breast cancer. I work with the same group of people. Again, they were this time looking at the kynurenine pathway for the breast cancer. To me, it was really important to be able to work on this project, because when I started working on this project, I mean, you can see that it's just published in 2020, but we've actually started this in 2017, early 2017. Believe it or not, I finished most of my analysis by mid-2017, but it took quite a lot of time for the doctors and chemical scientists saying, and they came back to me, asked for more analysis. So it took us 3 years to finally finalize the paper and submit it. So we submitted at the beginning of this year, and was published just before the end of the year, because the review also took quite a lot of time. And never explored before for breast cancer. So it was really important to be able to do that. That's what we've done. In this one, we had 2 cohorts. The first cohort had a control group, whereas the second cohort didn't have the control group. As well as the control group, they also had 3 different types of breast cancer. And one of these breast cancer groups are a really dangerous one. The other 2 are similar. And not as dangerous. So it was really important to be able to predict the really dangerous breast cancer group, so that patients could be diagnosed earlier and things could be done to save their lives. They had the blood collection before the surgery. They also collected tumor tissue before chemotherapy, and both of these were analyzed by different scientists. And then I received the data in batches when they came. So I work with that. I guess I said all of this. Interestingly, I don't know what am I doing, but whatever I do, C5-3 seems to be the best model, the things that I'm fitting in. Maybe because it's much more simpler. In this case, I also tried neural networks, and I also tried linear discriminant analysis, but C5-3 came up to be the best one. And I did tenfold cross-validation, and I did pruning so that I can prevent overfitting as much as possible. And with the model, the best model we identified, we were able to predict control group 36%, and the one of the subtypes of the breast cancer, which is the most dangerous, this TN1, triple negative, 66.4%. You wonder why this big discrepancy here? Because what I've done is I've actually gave more importance to be able to predict this group compared to other ones. So I used the misclassification cost in my model building so that a triple negative could be predicted as accurately as possible. So when you use that misclassification cost, what happens is the group that you chose is the most important, is more accurately predicted, but overall accuracy goes down because some other cases will be wrongly predicted. But we thought we can live with that because this triple negative causes life shortage, whereas if we misclassify the others, with a few more tests, patient could be identified not having triple negative. So therefore, their lives not in danger. So more lives could be saved by correctly predicting triple negative. What I had to do, because our second cohort didn't have control group, and also control group patients for one reason or another were much younger than the breast cancer groups. So to be able to have a consistent training data and testing data, and also similar cohorts, I have excluded control group. So therefore, the thinking was, we don't really necessarily want to differentiate between patients not having any breast cancer, but we would like to differentiate between the patients having different types of breast cancer. So that was the idea. So more for prognostic purposes. So that's how we framed our analysis. So in that case, I remodeled my data using the training set, and triple negative had the sensitivity of 95.2%. And 62.2% in the test data set. You can see that it goes down in the test data set. But what was important is the model was 44% more accurate than randomly allocating observations to triple negative or non-triple negative group. Now you can see I'm talking about 2 groups of breast cancer, whereas at the beginning I was talking about 3. The reason for that, when I talk more and more with my research colleagues, they told me that this is the most important, and there were small number of observations in these 2 groups, and therefore the model was struggling, and the difference, the shortage of life difference for the 2 breast cancer for non-triple negative was not huge. So therefore I grouped them together, so we had a binary outcome. So this is the decision tree that we came up with, or this model produced. And you can see that, okay, let me just see the color coding. The triple negative, as you can see, small number of observations have triple negative, and non-triple negative, which includes these 2 kinds of HER2 enriched and luminal, 2 different kinds of breast cancer. When I said small numbers are in these, I mean that group, one of the groups had small numbers, but my colleague said it's not detrimental to merge them, so that's why I merged them. So you can see that we can quite easily predict different kinds following the path of different chemicals in that kynurenine pathway. And you will also notice that compared to multiple sclerosis, we were this time looking at individual, only individual biomarkers like 3-HAA, but we were also looking at the ratios of them for some of them. KYN divided by TRP, or AA divided by KYN. What I would like to also say that I didn't just include the ratios, but I included individual ones as well. But what happened with the modeling is, in some cases, the individual biomarkers didn't come up to be important, but the ratios were important. Somehow in the chemical world, the ratios mean more in some cases. And in some cases, just having the individuals are more important. I'm about to finish. Okay, I'm just checking the time. I have 3 minutes. Okay.
So, Aisha, it doesn't matter. Please, you can go ahead. It's okay.
Okay.
Yes, yes.
So with this model, with triple negative breast cancer groups, the accuracy was 95.2%, and it was quite high, and it was very good, and it was comparable with other ways of doing the identifying which group the patients belong to. And the other ways are clinical ways, which require quite a lot of other tests to be done for each patient, not just the blood sample or the tumor sample. So it was important to be able to do that. And what we've shown is that we weren't able to discriminate between healthy and non-healthy breast cancer and non-breast cancer, but we were able to show these biomarkers helps us to discriminate between triple negative and other types of breast cancer. And this could be used by the doctors for deciding which patients have triple negative so that the treatment could start much earlier. Now, I'd like to have some closing comments regarding machine learning. It's really hyped up. It seems like in some aspect it's the only way to go, and computer scientists are spending quite a lot of time and energy developing new models. We statisticians should not shy away from them, but we should be careful. Here is one of the things happened in Australia in 2016. Mainly computer scientists were working on that project. Tax Office and Centrelink, which is our government organization that gives money to people who could be disabled or who are unemployed or who are studying towards the payment from the government. So in the news we saw in 2016, February, people were getting overpayments, and they were identified through applying machine learning techniques to data they had. They have used Australian taxation of data and any data they could get from these people from other government organization databases. Was that a good thing? But what happened not long after, I mean, I have 1 year later, just presenting you 1 year later, what we have seen in the news. But until then, there were so many discussions as well. What happened is they have identified people who've done absolutely nothing wrong, as said by the politician. They've done absolutely nothing wrong. Using the data mining techniques and machine learning techniques as a filter to further investigate would have been a good thing to do, but they have sent them automated letters saying that you owe the government that much money and you have to send it back. So this year, or sorry, 2020, many people were paid by the government for compensation because they were sent these letters. So they have wrongly identified many people saying that you were overpaid. Machine learning is great, but without human interaction at the end or without checking what is happening really, it might cause some problems. So that's one of the things. And we also saw in 2016, FBI was trying to get the data from us, supposedly catch some terrorists. And iPhone was, or Apple's unhackable iPhones and things like that. Just think about yourself and your phone and what kind of information is stored in your phone. Do you want anyone to be able to access to this data and public domain display what's in your phone? I mean, none of us are terrorists, none of us doing anything bad, but we have our own privacy and we possibly don't want everyone to have access to our data. So it's really, really important that we have to be careful of this privacy and confidentiality of the data using machine learning techniques. I'm going to just have one last say I like this coming from a Canadian philosopher. He says that a quiet statistician have changed our world, not by discovering new facts or technical developments, by changing the ways we reason, experiment, and form our opinions. I mean, I see myself as quite statistician in the sense that I have not developed any of the machine learning techniques, but I'm using my statistical thinking and statistical ideas when I'm applying machine learning techniques to any data set that I analyze. And I think it makes a difference to have a statistical thinking when you are using a machine learning technique. These are the 3 papers I have used for my case studies. And thank you very much for giving me this opportunity to present. That
Thank
concludes
you
my
very much.
presentation.
Thank you so much, Aisha. That was great. Okay, now we have the question answer session. So anybody who has a burning question, please go ahead. Dr. Alireza, do you have a question?
Thank you.
Yes.
Assalamu alaikum.
Walaikum salam.
Thank you very much. Thanks for Dr. Aisha for her very good presentation about the machine learning. We used a lot of things about her talks. I don't know. I don't have any question about that.
Okay, it's fine. We'll be having your workshop coming in a short while. Okay, I would like to ask other people, Dr. Kulsoom, Dr. Shakila, anybody else who has any question, could you please come up with your questions? Excuse me. Anybody else, please? Otherwise, I will be putting a question, but I wanted some other people to participate in this session also. You have no question whatsoever? All right, Aisha, please tell me, now that's COVID-19. So machine learning is being used for this thing all over the world, or at least in your country? Tell us something about this one.
I mean, COVID-19 is more like time series analysis with some predictors. One of my colleagues is doing it. He is working on that area, and he was able to really predict what's going to happen in different states of US and also in Australia. The examples I showed you are mostly the classification. So COVID-19 data sets are quite differently collected in different countries in the world, and even within Australia, different states collected data quite differently. And what we don't have access to in most of the cases is patient characteristics. So therefore, it becomes more like time series data that you just follow it through and see what's going to happen. But yes, there is also data mining, machine learning techniques available for the time series data. I have not looked at the COVID-19 situation at all. I haven't analyzed it, except that, as I said, I have worked with a colleague who is working on it. He's done most of the analysis, and he was just asking me whether it's making sense, and we work together. And the predictions are very good, but mainly time series. The reason I haven't done any analysis, I mean, firstly, you need time. And this year we moved all online teaching. Everything is online. And we were given like 8 days to convert everything in the first semester here in March. 8 days to convert everything to online, which is not possible. I mean, we've done a couple of weeks of transition, and then we continuously work how we're going to assess the students, what we can do. And because we were in lockdown, students were more active sending the emails, especially after the assessment results are released. Like every time I release an assessment result, 2 days from 9 a.m. to 5 p.m., I only answered student emails because I had more than 1,000 students in my class. I'm not complaining about it, but that was my 2020.
Yeah. Actually, this thing that you said that you don't have, I mean, we don't have data about the characteristics of the people who are having the COVID-19. I mean, I'm trying to say that as some people, they say that they don't have much problem. It's just like just a little bit of effect, but for some it is so serious. So how could, I mean, machine learning should be able to help in that, right?
Absolutely.
Yeah.
Yeah, absolutely. But we just need the data to be able to do that. Like if I don't know where I can get data for that for whole Australia, let's say, if we have an outcome variable where patient died due to COVID-19 or really impaired versus patient recovered, it's not a big deal. But when I said we don't have data, I mean not the art result, but comorbidities of the people, like whether they had other diseases and I don't know, some other chemicals in their body, the analysis been done and things like that.
Is it not possible to conduct a survey? I mean, we could approach those people who have had this experience and or those who died, if their relatives could provide that.
Right now, I believe the data is already collected or in the process of being collected, but it's not released publicly. My daughter works in health and wealth, Australian Health and Welfare Institution, which they basically aggregate public data from different states and different databases. What she was telling me that in Australia, each state used different way of collecting data. Just recently, a couple of months ago, they started moving a national way of collecting data. So when the data is available, absolutely, we can do things like that. And it will be really good to be able to see what characteristics causes people to suffer more. And also, I think what's important, Saleha, it's important possibly to collect data after people are immunized. When they are immunized, what will happen, whether they will have the illness and get over it very quickly, or they will have the illness but still suffer. So, and especially given that we have different kinds of immunization possibilities. We have this Pfizer immunization, and we also have the Oxford one, and there is Indian one, and there is American one. In Australia, it seems like different people will get different vaccination because you can only get so many doses of it. And I think I'm in a group, more than likely I'll get the Oxford vaccination. We don't know which one is more effective. I mean, in the test, they know, but then again, when it's applied to not healthy people, because they only did the analysis on the healthy volunteers, but when it's applied to everyone, we don't know which one would be more effective in certain circumstances. Absolutely great research areas, but we need some time to bring the data together, and yes, we can do that.
All right. Thomas, we have Thomas here from Kenya. He was just writing in the chat. Would you like to put forth some question? Thomas?
Not really a question. I was just following the discussion about COVID, and I kind of found it's a very similar occurrence like with Kenya. We don't know their traits, a lot about them. We only have aggregated data like national or regional. So you can't know whether one person is from one counties in Kenya. You can't know whether one person was from one county, died from another county. There is very little you can really say about COVID apart from just the national aggregate. It makes it, for someone like me, it's a bit uncomfortable because I would really love to have some questions answered, but I can't. We only depend on what the government tells us.
Yeah.
So I do feel, I think her name is Ail. Yeah, I do feel a predicament with COVID data. Thank you.
Thank you so much for your input. Aisha, I have another question. You talked about the importance of the privacy of the data that we are generating on the WhatsApp and on the, on all these things. So this latest thing that I'm hearing for the past 2 days, that they are going to have some privacy. I don't know what's going to happen. Can you comment on that?
I mean, to be honest, I haven't, I got the same thing when I updated my telephone WhatsApp app, and it just popped up saying that things are changing. Do you agree with this? I don't know what they're going to do really, but I have my family in Turkey. To be able to talk to them, I use WhatsApp. I can't really move over encryption. So I need to look into more detail to see who they are planning to share the data with. I don't know, but I can't move away from WhatsApp because it's important for me to have communication with my family.
Yeah.
Yeah.
Well, there's so much more that can be discussed. We can go on and on. It's so interesting. But we have to move on now with the workshop. Yep. I do want to share with everybody that the president of IASE, the current president, Joachim, he has written to me that he will be joining, but he will be a bit late. So Aisha, if you find time after about an hour or 2 hours, maybe you can still come back and join. Okay. Thank you very, very much. And if you want to stay, that's a great, great pleasure. And I want to repeat that, you have done it for us 2 times, simply because we did not have enough time left last time. Yep. But I'm so delighted that this has now been done. So thank you very much. Thanks.
Thank you, Saleha, and enjoy the rest of the day. It's 9 p.m. here, so I think I'll leave you alone.
Okay, right. Yes, you need to rest. Thank you. Okay. Thanks.
Bye-bye.
Bye-bye. So now I can go to the plan and to say that after this very, very informative talk and interesting Q&A session, now is the time for the commencement of the 3rd workshop on machine learning to be given by Dr. Reza Ali Belaghi and Dr. Alireza Safariyan. So after some time, we will have the short break. The time that I've written here is 3:25. So we have about 30 minutes, I think. So please now tell me, will Alireza be starting? Would you be starting, or will it be Dr. Reza? Alireza, are you going to begin first?
Yes.
Okay.
I will continue my talk about the regression at first. In the last of the previous session, we talked about the regression, but it was not finished. I have to continue that. After this section, Dr. Reza Arabi will continue in the principal component analysis and the clustering analysis.
Okay. So would you like to share your screen now?
Yeah.
Okay.
That's right.
Yes, fine.
As we talked about the regression, the king of statistical modeling is regression because it's very useful and very applicable in the most of the data, and it's very extended in the statistics models. So we introduced about the regression models and its some properties, how we can apply that and fit to our data. We talked very little about that. So I want to complete my talk about it. And for example, when we have only one predictor variable, for example, x1, we use the simple linear regression. And when we have much more predictors, for example, x1, x2, up to xp, we need multiple linear regression. When we want to use multiple linear regression, you know, we have some challenges about these models. For example, we see that sometimes the predictors are very much more than the observations, and some collinear with each others. So you know that we used to use them in the previous years. So the statisticians try to find the new new models, new methods that can overcome to these problems. Much more of the data in the nature, our predictors are very much more than our observations. For example, in the medicines, you know, when we want to apply models to our diseases, you know, we have very high dimension of the genetics problem, genetics predictors, that we can use them to model our the disease problems and so on. So here we need to find very good models that can explain about these variables and summarize these variables and find new diagnostics properties. So if we use the multiple linear regression, we have three variations that they are predictor variables, and all of the variations that we can explain them from predictors or not. For example, in here you see the SST is that all of the variations that there is in the Y, our response variable, and SSR, some of the scores of regression model, that the variations that model can explain about the Y by predictors, by X predictors. And here we have SSE variations that predictors cannot explain the Y, the share of the variations not explained by the regression model. So if we want to analyze the model, we want to define that how much our variations in the data can explain by the model. So we try to use R2. This R2 is very famous in the regression. It shows that how much of the variation in the model can explain by the explanator that it's used to different. We need to use R2 adjacency to compare this. And another thing we want to find out how when we use this model of regression, is that true or not? We use the F statistics that can use in the goodness of fit model. If it is greater than the F alpha, it will be good model. But if there's not, the model will not be good in the fitting to the data. So here we have a lot of new methods in the regressions. After the linear regression, we have polynomial regression, support vector regression, decision regression, and some others. We will talk about the ridge regression and lasso regression because they are very simple. And at first of the new methods, they are very useful. For example, we want to subset select some predictors and in high dimensional methods, and or ridge regression that can help us in collinearity variables models. As you know, the linear methods for regressions are at first of them are is ordinary least square regression, and the next is subset selection and shrinkage methods. Subset selections are traditional methods, you know, forward and backwards can help multiple variables. We need to shrinkage methods to find them to fit the regression model. Another method to finding the regression with these problems is that principal component regression and partial least square regression, that they help us to find the model by directions vision. Another linear regression was that logistic regression and linear discriminant analysis that you see in the previous section of the workshop. So here, if we don't have any if we don't have any collinear evidence about our data, we can use this methods. You know that these methods were very useful in the traditional data. If you didn't use any collinearity in about the data, they are very useful. But we talked about the collinearity. Collinearity is that when variables are correlated to each others, we need to find another method. At the past of the age, it was very simple to dropping these correlated variables to apply the traditional methods. But in this decade, some statisticians found very good methods that we name the shrinkage methods that helps us to find regression model by using these correlated variables. How we can detect the multicollinearity in our data? We can use we can calculate variation inflation factor, for example, VIF. We call VIF. If the VIFs are greater than 10, we can say that there is a serial problem. Or we can use eigenvalues about the variance of x prime x, we can find that if the eigenvalues are less than 0.01, we can see the variable. We can conclude that the variables are collinear. These counts, they are very experimental, and they are not fixed. So sometimes 15 or sometimes 10. For example, for VIF, sometimes is greater than, or sometimes for greater than 5. It's very depends on to our problems. If we want to find different regression models, we should assess the models by some criteria. The criteria that are very similar, very famous in the regressions and the models in the statistics, is that residual mean square and archaic information criteria, or Bayesian information criteria, or malus CP. They are very useful in comparing our models. Rich regression models try to minimize the penalized regression, penalized residual sum of squares. As you see here, we only add a lambda sigma beta j on power 2. We use this to restrict our coefficients, to control the coefficients, to find the model that can help us model that with much more variables than our observations count. If we estimate the coefficients from this model, our coefficients will not unbiased, but mean square of error will be small than the OLS estimator. So we have to add our bias in our estimators to make small our MSE. Okay, it helps us to shrinkage our regression coefficients if our number of predictors are greater than our number of observations. Lasso estimate model is very simple, similar to rich regression. Only the things that change according to the rich regression is that we use abstract of beta j's in this penalized function. So we cannot find closed form for the beta j. We need to find the numerical method to estimate our coefficients in the lasso regression. If we compare the lasso regression and the rich regression, you see that the lasso regression is constrained our coefficients by this shape. You see that it's very similar to square, and but in the regression of rich regression, it's the constraint is similar to circle. But less lasso regression can make a subset selection of our data because it can find the betas with exactly 0, but Reg cannot find the subset selection because it cannot make some coefficients equal to 0. If we see the coefficients of these models, you see that coefficients of lasso can be 0 exactly, but in the ridge it can approach to the tends to the 0, not exactly 0. So the subset selection of the lasso is very useful in the fitting the data to the data in the models. Okay. I want to in this section to, for example, use the Boston data in the R studio. You see let's show you the Boston data is the median price of the houses in the Boston. That is the 14th columns of the data is that the price of the houses, and the others are the predictor variables. Can we use we use them to predict a new price of the data if we want to predict. Here the names of the Boston you can see. Dimension data is that we have 14 attributes and 506 observations. And first of all, we should scale the scale the data, standardize our data. We use the scale Boston. So at the next, at the first, I used only one LSTAT, lowest stat of the predictors to show the simple linear regression. In the summary of the linear regression, you see that we have two coefficients intercept. That is our constant, and the LSTAT was our slope. That is minus 0.95. These are significant in each of the scientific codes, alpha, and the multiple R square. You see that it is 5.554. That is, and that it shows us the model can explain by LSTAT by 5.4% of the variations in the model. And F statistic is that 601.06. Our test statistics, and p-value is less than 0.05 and 0.01, then the model is significant. We can see our coefficients by this code, and they are similar to finding the coefficients. Another thing, we want to find the confidence interval about the coefficients, and or we want to predict some responses for other amount of LSTAT variable. We can use this function. You see this. This is the predict for the sum of amount of LSTAT variable. Okay. The plot of the L stat versus price of the houses in the Boston, you see this is not very linear. There is evidence of nonlinearity in this data. Then we should have models with nonlinearity of methods. Okay. At the last of the model, we should test our residuals. You know, the regression model, the residuals should be normal distribution and independent. We can assess them by these plots. Now I want to use the model for my multiple regression. Then we want to use predict our response variable by all of the predictors. The first method I want to use is that backward. Then at first at first step we have all of the variables in the predictors, and in the backward tries to find the variables that they are not significant and should be removed from the model. As you know, as you see here, at the first, our model contains all of the predictors, and the next the next model, the age is that the variable removed from the first model, and the next model shows that the other predictor is induced removed from our model, because these predictors have very small correlation with the response variable, and when we get rid of out these variables, the AIC can improve and get smaller. If we use the forward, we tried the forward and start with the model only with constant. So it tries to add the other variables to the model step by step. I tried here only for 3 steps from these variables. Scope is the final variables. We can use them to import in our model by forward stepwise. In the summary, you can see after making 3 steps in the forward method, the only L-stat and RM and PT ratio variables can import to our model. The forward regression can help us in the models with very much more predictor variables, and it was very useful about this data. Summary of the model you can see here. The final model in the forward regression is that here you can see the residual error, standard errors, and multiple R squared. You can see the 67% of the variations in the price of house can explain by these 3 variables, 3 L-stat, RM, and PT ratio variables. And the model is significant because the p-value is less than our alpha. And The other method, traditional method, is stepwise. That stepwise regression use both of the backward and forward methods. And at first, it tries to remove some variables and then test the variable that shows if the variable can remove from the model or not. And then if can remove, it will remove from the model, but if cannot remove, it remain in the model. You can see the steps of this method in this step AIC, and step ANOVA can show the results of the model. At the steps of the stage-wise regression, you see that at first only we have these variables, and which one of at first removed from the model, you can see here. At first, age removed from the model, as you see in the backward regression, and the next step in this variable will remove from the model. And the final model is that very similar to backward regression. These are the traditional methods. So if we have much more variables predictors, so we should try to assess the VIF collinearity about the variables. VIF can help us. We have the variables. You can see some variables, for example, the variable tags. These are very much more than the 9 or 5. As I said about that, if the VIF is close to the 10, we should collinearity about the variables. And another thing that we had that helps us to show the collinearity is that matrix of correlations of the variables. You can see here. The some of the variables have collinear with each others. For example, the blue ones of these circles here. For example, here and here, some of blues are very correlated to each other's variable. So we should try to find the new shrinkage methods to fitting the model. Another thing was that eigenvalues of the variance of X. I should make it X. It helps us. Let me show. Okay. In this, you see that eigenvalues, some of them are very close to 0. For example, here it's very small, and for example, here is very small and close to 0. Then they are evidence of the collinearity in the predictors. Another thing was that SQRT or root of the as I showed you here, you see that root of this proportion is less than 15. It can be show that they are collinear. Here show that it is that 9.82. but it's very close to the 15. Then we can agree about the collinearity in these variables. So I want to fit the reach and lasso regression to this data. At first, I use the cross-validation and make a two-part for data to train and test. Okay. At first, I use the model to train data. You see that in the lasso, you know, if we use the alpha equal to 1 in the GLMNet function, we can apply the lasso function. And if we use 0, we can apply the reach regression model to our data. At first, we use the 1 to applying the lasso function. You see that some of the variables are exactly 0, coefficients are 0, so we can make a subset selection of our and the next, if we use cross-validated of the GLMNet, you can find the best lambda tuning parameter of the model in the lasso function. The best lambda is that the lambda that minimizes our mean score errors is that here our best lambda is that 0.003, and we use that to apply to fit the data model to our test data and find the MSE for lasso in the test data.
Dr. Alireza, how much more time do you need?
Only 5.
It
only
is
5
time.
minutes. Only 5.
Okay.
Okay, thank you.
Sure.
You see that the MSE of lasso model is that 0.27, and similar to reach regression. You will see that the MSE of reach in the test data is that 0.28. You see the reach of the MSE of the reach is a little greater than the lasso. We can compare the lasso and the reach. You see that in the lasso, for example, induce variable and the age variable coefficients are exactly 0, and we can take and we can remove them from our model. And but in the reach regression, we don't have any variables very close to 0. As you know, in the coefficients of reach, you see that the right side of this plot, we show the this cut of the plot is for OLS, and these are the back of the mouse to 0. Another thing, the lambda in this we have in the model, in the equation model. So the lambda is when lambda goes to 0 in the reach model here. When lambda is go to 0, then we should have a similar our OLS method. But if the lambda is goes to infinite, then the beta j's goes to 0. You can see them here in this plot. I tried to another machine learning methods to show there's majorities about the predicting the models. I tried to use tree method and random forest method to predicting the test data, and boosting method. At last of these methods, we can see their MSEs in this plot. Let's say it's run. It's running. Okay. Oh, okay. You can see the random forest is smallest MSE in the predicting the house prices in the test data, and the next is the boosting, and after that was lasso and reach, but the regression tree was not very good in this data. Another thing that I want to tell you about the machine learning, we only introduce the useful methods in predicting the response variables. We don't have we never have very best model in fitting to our data. We only used we only train all of the methods to find the best model between them. Thank you very much. Dr. Arabi will go through the next session to the principal component analysis and clustering data.
Okay, thank you very much, Dr. Alireza. Thank you for that. It was very informative and such interesting and intriguing graphs. Also, I've enjoyed a lot. So now I think I will share my screen.
Okay.
Yes, you could perhaps unshare and I can share my screen now. So, ladies and gentlemen, now is the time for the commencement of the short break, and anybody who needs a break is most welcome to have the break. But I do want to request all those who are teaching and who have students, you're meeting them every day. Nowadays, maybe it's happening online, but you are in touch with them. I would like to share with you, and I will request my colleague, Dr. Sharka Hashmi, to assist me in this. So let me present to you a little bit about the ISLP International Poster Competition. Before that, I just did some Google. I put this question on the Google as Alireza was talking about the regression. I thought that maybe somebody might be slightly, may have this question: what is the connection of regression with machine learning? So it says here, to solve such types of prediction problems in machine learning, which of course you will click at the bottom and then you'll find out which particular types of prediction problems using machine learning you want to do, for which you would need regression analysis. Regression is a supervised learning technique which helps in finding the correlation between variables and enables us to predict the continuous output variable based on the one or more predictor variables. And just, you see, what Alireza has given us is much, much, much bigger and so much detail and all that. But, for somebody in this group who might have thought that I'm not clear as to what is the connection, I thought I just wanted to point out that you could then, we could study more on this aspect. So now, as I said, this is the basically a short break, but I'm requesting some of you to please stay on. So, ladies and gentlemen, this is the International Statistical Literacy Project. This is the website. You can always, just write this on the Google and you get to it. And this is actually a project of IASE and also of ISI. ISI, as many of you know, is the International Statistical Institute. And you can consider that as an umbrella under which there are so many different associations. IASE is one of them. This is the one, the International Association for Statistical Education. But then there's so many others. IAOS, Official Statistics, IASS, Survey Sampling, IASC, Statistical Computing, and others. Now, ISLP, this project is one of the projects of ISE and ISI. And they have these competitions along with other things like publications and other activities. They have this competition going on. And this has been on for a number of years. And this time from the forum of PISTAR, I, as a country coordinator of the ISLP, I would like me and focal person, Dr. Sharka Hashmi, we would like you to participate in this competition. So I just want to say that I've put some things here for you. This is from my side. I think it is an exciting opportunity for the students of intermediate and bachelor levels because it will enhance their knowledge, creativity, and skillfulness. And the participation in this competition can turn out to be particularly valuable in this time of COVID-19, when normal studies are being hampered due to the pandemic. It can turn out to be a highly educational, enriching, and horizon-widening experience. And, to bring out the inner talent and potentialities for participating in this healthy activity, I think it will be truly worthwhile. I want to show you the website, the addresses of these websites. And I also want now to say, and after this, I will request Dr. Sharka Hashmi to proceed with it, that this time the topics are environment, biology, and sustainable development. So the posters would reflect or illustrate the usage, analysis, interpretation, and communication of statistics or statistical information with reference to any of these three broad topics. Each one of them, as you can see, is very broad. So, it's very, I think it's very easy to find some topic of interest within the framework of these three broad topics. So, Dr. Sharka, would you like to continue from this point? Dr. Sharka? I think there might be some connectivity issue because I could see.
Okay, thank you so much, Dr. Saleha. I will continue from here.
All right. So let me do the slideshow again, and I will now proceed to the next slide.
Okay, ISLP International Poster Competition. There will be national competition within each country involved, followed by an international competition to determine the overall winners. These will be announced and the posters displayed at the 63rd World Statistics Congress of the International Statistical Institute in July 2021. Although there are three categories of the competition: lower secondary schools, upper secondary schools, and universities, or universities of the applied sciences, bachelor level students. The PISTAR team is launching the competition this year for the second and third category, that are upper secondary schools or intermediate level, universities or universities of the applied sciences, bachelor level students. I would like to invite you to encourage your students to actively participate in the national competition under your guidance and supervision. The competition is open to teams of 2 to 5 students each, and you will be happy to note that there is no fee for registration. In the competition, prizes for the upper secondary school or intermediate level categories are Euro 450 for the first position, Euro 350 for the second position, and Euro 200 for the third position. These are the prizes for the intermediate level. While in the university category, there are grand prize for the international winner, that is Euro 2000. In addition, the JMP from SAS will reward with an honorary mention the university team, which will have best applied the JMP software in their work. This is the software which is involved in the in making the posters.
But I would like to interject here. They don't say that necessarily you must use JMP. You can use any software that you might want.
There will be a national competition in the Pakistan to be organized by PISTAR. The competition is open to teams of 2 to 5 students, and each such team is to be registered with PISTAR by the teachers or faculty staff who will be supervising the students. The deadline for the registration is Friday, 15th January 2021. So 4 days are left. The period for the preparation of the posters is until Tuesday, 9th February 2021. And the deadline for the submission of posters in digital or soft form form is Wednesday, 10th February 2021, 5 p.m. All submissions in the form of email attachments to be sent by the supervisors at the following email address. PISTAR will organize the national competition on Friday, 19th February 2021 during the 18th International Conference on Statistical Sciences to be held on February 18 to 21, 2021. Subsequent to the announcement of the winning poster, PISTAR will upload the national winning poster on the ISLP website before the closing date of international competition, that is 28 February 2021. Subsequently, an international jury will be judging the finalists from various countries and for choosing the winners of the ISLP poster competition 2020 to 2021. I am optimistic that you will be encourage your students to take keen interest in the competition. Me and my team will be looking forward to receiving a number of high quality posters from your esteemed institution. As soon as we receive indication of interest from your side, we will sending to you a registration form. And the deadline of registration form, I mentioned you that it is 15th of Jan. This is the look of the registration form. We will send this registration form to your institute whenever you will show your interest.
Okay, thank you very much. Thank you very much, Dr. Sharka. So, ladies and gentlemen, I just want to repeat that you don't have to worry that there's only 4 days left. So how can we do it now? Because you see, as Dr. Sharka said, it is simply the filling out of this form that has to reach us by the 15th. And we cannot extend this date because this deadline has been given by the ISLP themselves. But of course, many of you know that I have already, me and my team have already sent hundreds of emails all over Pakistan. And some of you must have seen this before. But even so, if somehow you were not able to do it before, even now you can get some of your students interested in doing this. I'm sure if you approach them, you will get some good response. And you just fill this form by the 15th, send this filled out form by the 15th. And after that, as it was said earlier, I just want you to see it one more time, that you have then how many weeks? About 3 or 3.5 weeks in order to actually prepare those posters, because the deadline for the poster submission is the 10th of February. So this was about this competition, and I hope that some of you will take interest. We already have some entries. Some people have registered, and we are happy about this, but we would want more people, even more than what we have now. So although this thing says completion of short break, but I think we can maybe, we can have 2-3 minutes more. So after about 2 minutes, I will talk to you again. Thank you.
Dr. Naghmi?
Yes.
I have a question.
Okay.
First of all, thank you, Dr. Sharka, for the detailed introduction of this ISLP poster competition that is to be held. My question is, Dr. Naghmi, that the students who would be participating, are they specifically the statistics students, or students from other discipline can also participate?
Any discipline whatsoever. There's no such mention on their website that it has to be a stats student. So all the participants of this workshop, all those people even who are not teachers themselves, you must, disseminate this information among your friends and relatives, because, everybody has young people around them. So Dr. Kulsum, of course, the stats students can do it, but then the environment or any student, any student whatsoever.
Thank you. And my next question is,
yes.
Thank you. Dr. Naghmi, my next question is, are there any thematic areas on which students can work, or is it again open?
I just heard Charka sharing with you the 3 topics, or was it myself who was talking about them? The 3
Actually,
topics.
I'm sorry for that because I've missed that. I just took a very small short break.
Okay.
So it might
all
be
right.
Delivered
okay,
at
all
that
right.
time.
No problem. You see, this is the one. I'm so happy that you're taking interest. That's the important part. So it is this, I'm just getting to that. There you are. Environment, biology, and sustainable development.
Thank you.
So, sustainable development, SDGs, there are 17 SDGs. So it's so broad, you can just take any area. I mean, it's very, very broad.
Definitely.
And the environment,
Thank you.
have so many different things. And I also want to say to the international participants that maybe your country coordinator of ISLP is also doing it in your country this year. So for Pakistan, this is the first time. But for other countries, it has been happening in previous years also. So, for example, Thomas, you could look at their website and find out if they have a country coordinator for Kenya, and if they are organizing this competition. Otherwise, if you don't see a country coordinator of Kenya on that website, you can probably let them know that maybe you yourself might want to become the country coordinator for Kenya. You have joined IASE. You have become a member of the International Association for Statistical Education. And I, as I was also vice president of this association for a year. So I'm delighted with that. I would like to encourage other people also to, to join some of these international bodies, because from my life experience, I can share with you that it is worth it. So similarly, Dr. Najla from Saudi Arabia, if you have some country coordinator, which you can find on the ISLP website. So I'm saying all this because I know that we have, mashallah, we have international participants here also. So I would like to encourage you as well. Just maybe 1 minute more. And after that, I will ask Dr. Reza to continue with the very informative workshop. Okay, I think we can now resume the workshop. Ladies and gentlemen, you were just hearing a lot of important things from Dr. Alireza Safariyan. I'm extremely grateful to you, Alireza, for all the hard work you have put in for making this easy for us to understand and to get the hang of some of the things we might not be aware of. And now, after your part, we are going to have Dr. Reza Arabi Belaghi, to continue with this level 3 of the workshop on machine learning. So Reza, would you like to share your own slides?
Yeah, thank you so much, Dr. Saleha. Definitely, I really appreciate your invitation and for such nice series of workshops and all things, especially the competition. And in fact, I encourage definitely my students in Tabriz to actively, in fact, participate in this competition. So they were asking me about the timing, and now I understand that firstly we need to register. So that is quite easy. Then we can continue with the other staffs and providing those materials and get ready for the competition. So thank you very much for your helpful information. And this is really
so now my students will be competing with your students. But it's a healthy competition. It's a healthy competition. Yes.
Yeah,
Thank you.
know.
Thank you so much for saying all that you've said. Thank you.
Thank you. So may I start, Dr. Saleha?
Yes, please do.
Thank you. So let me share my screen. So what am I going to talk about today is something called, we say, unsupervised machine learning algorithms. So like without going further, I'm going to share you an Excel sheet of the data that I recently got to analyze. So I wonder if you see my screen. So what I had is 2,500 genes or even more. I recently got like genes of almost 20,000 variables or 20,000 genes or microRNA data. Then, so we don't have the target variable here. So what we want to see, we want to know what this kind of, in fact, tremendous amount of genes says to us. So what can we detect from, this much of observation? So we have 10,000 genes, 2,500 genes, and what we have also some cases, patients, patient. So all we need to do is we need to extract the data from this kind of variable, a lot of variable. And so, for example, is this genes telling us that there are 3 types of genes, maybe benign, maybe malignant, and maybe other types of genes? Or how can we extract this knowledge from from this kind of data set? So here it is obvious that we don't have the outcome variable, so we don't have the target variable, we don't have in fact the response variable. What we have is we have a whole bunch of, in fact, variables that might be correlated somehow together. And now the question is how we can understand the pattern in this data, how we can detect if there is a cluster of genes, or if there is a cluster of observations, or what kind of what kind of essence information are behind these kind of variables. So this is called as such as unsupervised machine learning algorithm that in fact I am going to discuss in this session. So in unsupervised machine learning algorithm, so let's define what is the unsupervised versus supervised. So far, what we have discussed was supervised learning. Why? Because we have the target variables, or in industry, some people says we had target variables. In medical science, we say we had outcome variable. In statistics, we say we have response variable. So on the other hand, we had in fact our X. So we had Y and we had X, and we want to predict Y based on those X. And then all we need, in fact, we wanted to provide, let me open my paint in a very simple way to say, we want to predict this Y, we want to have a function like F. So then I want to have, I want to predict Y. So given this X, right? So all of those techniques are relating to finding this function that I am going to say F hat. So once I do have F hat, then in fact, for any given X, I can predict Y, right? So since I had Y, then we call this one as a supervised machine learning algorithm. So we had, in fact, here, so if these are my Excel sheet, so I have Y here, my response variable, it could be binary variable, it could be multinomial variable, or it could be a continuous measurement. So whenever it was a categorical variable, so it can be a categorical variable, I am going to write cat, or it can be a continuous variable, right? So if that is a continuous, so if that is a categorical variable, then we go through like classification. So we go through classification approaches like we discussed. So we had decision trees, we had random forest, we had different kind of classification method. So on the left hand side we had X, right? So these are my X. So and I want to learn from this data set. Then for any new X, if I say like X new, then I want to see what is my Y new hat, right? So I want to have a prediction for Y new hat. So, and what we discussed is that, so if the Y, if the outcome variable was, in fact, was the categorical variable, then we went through classification. And Alireza told that if the outcome variable is continuous measurement, then we go through regression analysis. So all of those techniques that we applied for classification, we can get help of them to have, in fact, regression as well. For example, we can have multiple linear regression model. We have random forest regression. We have decision tree regression. We have lasso regression, and so many methods. And now the thing is, if somebody asks us, okay, in medical science, which one we should do? The question is, we should do training and testing, and then we see which method provide us better results. So in fact, that is quite critical, because later on, after we developed our machine learning algorithms, we want to use them in practical and in real life situation. So these things are going to supervised learning. But in unsupervised learning, what I do have is just I do have my X. So I have like X1, I have X2, X1, X2, and until I do have XP. I do have P predictor, P variable. I don't have C, like Y is missing. I don't have Y. What I am going to do is I'm going to learn the pattern in this X. Maybe I can do some clustering. Maybe I can do some principal component analysis, or maybe I can do a factor analysis at the end. On the top of that, all of them, I mean, there is something very interesting science recently came out. It's called a structural equation modeling, or SEM, which is in fact quite interesting. And I'm going to just introduce what is the SEM methods used for, and how in fact is going to be analyze the data, you know, very complicated and structured, unstructured data. So this is the way that unsupervised machine learning working. So as we mentioned in the unsupervised learning, we have learning useful structure without labeled classes. So if I wonder you see my PowerPoint, but I hope you can see. So in supervised learning, we want to predict the outcome variable. In unsupervised learning, we want to learn useful structure without labeled classes. So we don't have labeled, or we don't have observations. So those three things that I'm going to discover in the workshop is clustering, plus principal component analysis, and factor analysis. So let me introduce with some example in R. So I hypothetically generated some data in R for clustering. So let's see, I do have my data like this. So I have generated data from multivariate normal distribution. And so you know univariate normal distribution. So in univariate normal distribution, the distribution of the data are quite symmetric around the mean of the observations. And most of the observations are mean plus minus 2 standard deviation. So that is the basic of the normal distribution. So I have generated, in fact, data from three-variate normal distribution. And let's see, this is my data here. So let's go through Zoom. So what I see is, I see there is, in fact, some observations are here, are close to each other. Some other observations are here, close to each other, and some other observations are here, close to each other. So what I mentioned is close to each other, in the sense that they are, in fact, close to a common center, right? So, and in fact, it is because I have generated the first data from multivariate normal from mean of 3 and 3, the second coming from mean of 10 and 8, and the third observations come from the mean of 20 and 1. So this is in fact the structure of my data. And now the thing is, so here I have generated my data from multivariate normal distribution, or three-variate normal distribution, and I see how I can generate the data. Oh, sorry, by the way, this is a bivariate normal distribution, not three-variate normal distribution. So because I can't depict the three-variate in 2 dimensions. So here I know how can I generate this data. But now in practical situation, we don't know how we can cluster these observations, or how we can get information from this kind of observation. So now the question is, why it is so important? So let me in Paint give you another example. Let's see that this is the scale of the marks for the students. So let's see that this is, so in our country, we have from 0 to 20. So 20 is the best mark, 0 is the worst mark. So we have some observations here, some students here. We have some students here around 10, and we have some other students here. So what we see is that if I want to in fact to get information about these students, what I can see is some students are here, some students are here, and the other students are here. So it tells me that there are 3 kinds of students, maybe those who don't study, those who have, study a little bit, in average, and those who are so smart students. And if I want to have, like some plan for those students, I want to see who are in the first class, who are in the second class, and who are in the third class. So these are some of the basic of the cluster analysis. And let me go through my PowerPoint. So in cluster analysis, for doing cluster analysis, we have some, in fact, some method of clustering. One is, or the simplest one is k-means algorithms. The second one is hierarchical clustering. So these two are some of the most widely used clustering. And in this session, I am going to introduce to you what they are and how we can use them in practical situation. So I want to tell you so much detail about in fact, the mathematical properties behind those kind of clustering, as they have well established in many books. So generally in clustering, what as I mentioned, we want to group the observations based on the similarities. And so it's kind of unsupervised learning because we don't have the labels. So, and this is in fact, this is another example that it shows us that it's been generated in by three different processes, and we want to label these three processes. So why it is so important? For example, in real life situation, group people of similar size together to make small. So we want to group people to make some clothes or t-shirts. So what we say is, like, we have some small size people, medium sized people, and large sized people. So this is quite, a good application of what about clustering. Or in the, so we say that we cannot have like a unique size that fit for all of the people. So it means that clustering really needed in some situation. Also in gene expression analysis, we want to see which kind of genes we do have. So some genes provided, some characteristics like they are benign, other ones are malignant, otherwise are maybe none of them. So it is quite important in marketing or segmentation of the customers according to their similarities. So these are some of the, in fact, the useful information about, practical application of clustering. In the history, in the science, we have, biology, psychology, etc. So all of them are kind of clustering. So what we have is, in fact, in clustering, we have two different kinds, as I mentioned. We have k-means clustering, and we have, in fact, hierarchical clustering. So what we want to do, we want to have interclass distance. In fact, we want to have interclass difference minimized. I mean, within the clusters, we want to have minimized differences, and outside of the class, we want to have maximized, in fact, differences. So in order to do clustering, we need to learn some of the algorithms. So I don't want to go through those algorithms, just I have mentioned them here. The issue with k-means clustering is that, so it is quite sensitive to outliers. So let's see, I do have two groups of observations here. One group is here and another group is here. So if this outlier is here, then we will have, two clustering, and this does not make sense for us. So these two, the clustering of the first figure, at the top, it's not a good classification, clustering, because we have an outlier. So what we need to do is we need to remove the outlier so that we can have these two clusters. So the best thing about k-means clustering is to use, in fact, is sensitivity to the outliers. So now let me go through my R and then see how we can do clustering in R. So I do have a data, iris data. And so I have the structure of my data. So note that for clustering, since we are, in fact, we are working with the distance, so we want to see which observations are close to each other. It means that we need to measure some distances. That's why mostly clustering is useful for when we have continuous observations. So there are some other, some development for the categorical observation, or even if we have a Likert-Diskert for our data, then we can still use clustering. However, the most widely used technique, the most widely data that clustering used was, in fact, the continuous measurement. So if I do have like the head of my data, I can see here what I have. I do have 4 variables, and I want to see how many clusters we can get from these 4 variables. So I can have, in fact, the pair graphs for these observations. So, which is not so much just, it shows that there is some highly correlated variables within my data. And now, these are some of the graphs that I don't want to go through them. So now what we need to do, in fact, in clustering is we need to, in fact, to normalize our data first. So we need to have unique, we need to have, common center and common scale for our data. Otherwise, the clustering will not make sense for us. So we need to have the mean for our data. For example, I do have mean. So I use apply function for my data, and then I use 2 for the columns because I want to have the column means or the variable means, and then the mean function goes here because I want to have the mean. So in fact, I calculated the means, I calculated the standard deviation. Now I normalize my data, and this is my normalized data. So once I did normalization for my data, then I calculate the distances. So with this function, I calculate the distance of the observations. So I can have the distance for all of the observations, and I can see here how they look like. So now, whenever the observations are close to each other, then we can use, in fact, clustering. We can put them in one cluster. So there are different kind of clustering. So one is called, as I mentioned, we have k-means clustering and we have hierarchical clustering. Let's look at how the hierarchical clustering will work. So once I did in fact distance for my observations, I can have hierarchical clustering for the distances. So what we learned so far here that is so important is we need to have clusters for the distances. So let's have the plots for this observation. Now this is something called dendrogram. So let me enlarge this plot and see how we can interpret this. So this shows that essentially at first we had 2 class of observations. One is the left-hand side of classes and another is the right-hand side class. Then if I go down, then I do have 3 clusters. So, and then if I go down and down, then at the end, I will find each of my observations in a single class. So this is one way that we can, in fact, interpret this dendrogram. So, but in fact, we don't go through the bottom because here I do have, as the, we have the number of clusters is equal to the number of observations. So it will not work for us. So how did this dendrogram produced? In fact, it started from here. It will look at these observations to see which 2 are similar to each other in the sense of distance. Then it clusters them into one class, one cluster, then goes up and up. So in practical situation, the number of clusters is in fact a mystery, and we want to know how many clusters we want to know. We want to have in our data, or how many clusters generally we do have. So if our data is, so based on dendrogram here, we can have, 3 clusters is good for our data. But k-means cluster, later on, I will show like how exactly we can specify number of clusters by some statistical approaches. So we will have mean square error of the observations. So whenever the mean square error of the observations is remain constant for some specific classes, then we stick those clusters. So in this dendrogram will show us that we should have 3 clusters here, but within each cluster there are subclusters as well. So now let's have another. So for hierarchical clustering, we have different kinds of methods to do dendrogram. So one is called average, another one is called this is the default from each class. This is called the maximum distance. So which in fact the best one is to use average. So the average or the average distance from the mean of the clusters. And if we go this way, then we could also produce similar clusters as well. So now we can have the members, cluster membership here. So, and we can have, in fact, we can have the number of observations in each class. So what we see here is that we have 50 observations in one class, 92 observations in the second class, and 3 observations in the third class. So this tells us that two clusters are enough based on this method of clustering. So, and now let's see how the k-means clustering will tell us. And before going to, so k-means cluster, in k-means cluster again, so yeah, I do have here. So again, I aggregate my, in fact, my data based on their means. So here is my first variable means, the second variable means, and the third variable, and also the fourth variable in the clusters. So we have the means of the variables in these clusters. And now we do have something interesting that tell us that how many clusters we should choose. So if I go this way, and so I want to have the mean square error of the observations to see if based on the number of clusters. So let's run this code and plot it to see how we can produce the optimal number of clusters. So what we see is that this is within group sum of square errors. So if we have only one cluster, then within a group sum of square errors is 600. So which is quite large. Now, if I increase the number of clusters to 2, then this means this sum of square error decrease significantly to almost, like from 600 to 200. So it's dramatically decreased. Then within 3, if I increase number of clusters to 3, there is a small, in fact, small variations, but a small decrease. So what we see is that, so based on my observations, and let's see, after like maybe, 4, 5, 6, etc., then the within group sum of square will not change significantly. So it tells me that 2 clusters are enough. So now what happens if I use 10 clusters, 15 clusters, 20 clusters? So then in this case, I will come up with something called overfitting. And then whenever I want to predict my observations in the testing data, then I will have, like a lot of misclassification errors. So it tells me that the best number of clusters is 2 or 3. So 2 is, to me, 2 is enough to have, more simple methods. So this is the way that how we can, in fact, find number of clusters in my data. So based on our observations, we have 2 or at most 3 clusters in this data. So now let's go forward to see. Now this is the way that k-means clustering works. So for k-means, again, we need to use clusters for the normalized data. So for k-means, for k-means clustering, I just need to use the k-means function, and I want to see what is my how much I want to specify the number of clusters. So based on my observations, 3 clusters is good. So now let's run the code and let's have the clusters. So what I see here that is that I do have, first observation belongs to the first cluster, second observations belong to the second cluster, and so on. So, and I can do, I can have a cluster of, table of the clusters. So what I see is I have 100 observations in the first class. I do have 34 observations in the third class, and I have 16 observations in the third clusters. So, and essentially in this data, because we know the truth in this data, we had three kinds of outcome variable. One was setosa, versicolor, and Virginica. So it means that the clustering works here, but the thing is that we can summarize this data into two clusters because most of the observations are in the two clusters. So this is the way that we can do clustering for our observations. And if we have a large amount of variable, whatever we have, we can use these two clustering method to extract some knowledge from the raw data. So now I'm turning to another, another talk is called the principal component analysis. Oh, sorry, Dr. Saleha, did you tell something?
Actually, no, it wasn't me. I think Dr. Itrat Batul Naghmi has joined just now, and the mic was not muted. Now it is muted. Thank you, Itrat. Apologies for the disturbance, Dr. Reza.
No problem. Thank you very much. So now, if you have any question from this part, then please let me know, and I will be happy to provide more information. So, and if you don't have question, then I can proceed with principal component analysis.
Yes, please do put forth questions. Anybody who would like to put any question?
May I put the question? This is Abdul Salam from State Bank.
Please.
Assalamu
Thank
alaikum.
you.
Go ahead.
Walaikum assalam. Thank you, Professor. You mentioned two types of clustering, hierarchical clustering and K-means clustering. I mean, when to use which type of clustering? Can you please explain it? Thank you.
Yeah, thank you. So, in fact, there are not only two types of clustering. We have model-based clustering as well. So these are non-parametric clustering, and we don't look at the distribution of the data here. So I never mentioned about the distribution of the data. So these two are the basic and the simplest method of clustering. So we have, model-based clustering, which is quite almost new. So I know a professor in McMaster University. His name is Paul McNicholas, and he's a great scientist. And his major is just working on the clustering. So now the thing is how we can which method we should use. To me, as a statistician, I will start with the simplest methods. So hierarchical clustering and K-means clustering, because they are quite non-parametric, they don't need too much effort. But if we do have, some complicated data that we cannot have, good clustering, then we could use other methods like model-based clustering. For example, I do have a picture here. So what we see here is that in the left-hand side, we have two different shape of the data, right? So we see this is the first cluster and this is the second cluster. So really these two clusters are different. And if we want to cluster, the base clustering method should cluster, these two figures in different ways. I mean, for two different classes as they are really, But if we use K-means clustering, then it will produce us the right-hand side figures of two clusters of the data, which in fact is not correct, because the true cluster, the true natural cluster are in the left-hand side. So which is not in fact coincide with what we have in the right-hand side. So still, the science is in the way to have, more interesting clustering ways. So, but I will start with the simplest method to see how, how can I identify the clusters. So, but if I can use, like those who, to make sure that we are in a correct way, we should in fact we should examine different methods like what we had in the supervised machine learning algorithms. So for any specific data, we will examine, because all of these techniques are data-driven methods. So it's not like mathematics that we can prove something. We just learn from the data that which one is better. Now we will propose different methods to see which one have better fit to our model. Then we will choose that one. And if the simpler methods provide us, the similar result as the complicated methods, that I would choose the simplest methods. Is there any question?
I have a question. Assalamu alaikum, Dr. Reza. This is Dr. Kulsoom Akhtar. I'm heading the statistics department at Kinate College for Women, Lahore. My question to you is that if we have a data which has the outliers as well as the missing values, so in that case, what do you suggest, that whether we should go for the traditional approaches of clustering or should we go for model-based clustering?
Yeah, thank you. That's a great question. So, in fact, outliers and missings are always, kind of pain for a statistician. So for missing observations, what we can do is, if we don't, if the proportion of missing is 5%, then we can remove them, right? Because we will not miss so much information. But if they are, large number of missing, then we should substitute firstly by multiple imputations. But the first place, before missing is, to somehow to remove the outliers. So because even if we go through the model-based clustering methods, in fact, there we fit some distributions, some mixture distributions for the observations. And if there is outlier, then fitting those distributions will not work, So to me, somehow maybe removing the observation, specifically for clustering, because they are somehow, working with the distances. So removing the outlier is better method. Because as I see, if we go through even model-based clustering or non-parametric clustering, they will make, pain for us. So after removing the outliers, I think the best way to dealing with the high proportion of missing is to use multiple imputation or to use KNN imputation. So multiple imputation means that we, in fact, we started with producing or predicting some missing values. Then we model the data. Then we do it for 4 times or 5 times or 10 times. So then we aggregate the results. So this is the nature of multiple imputation. So imputing, analyzing, aggregating. So this is the way. And KNN imputation is also interesting methods, is non-parametric methods that, use it's a kind of machine learning algorithm to predict those missing observations and filling those observations, and then, in fact, do a statistical analysis. Recently, I saw a paper published. It shows that a random forest method is the best approach to fill the missing data. However, it's quite, computationally expensive when we do have large amount of observations.
Thank you for the detailed answer, Doctor.
Thank you. Is there any other question? Okay, so let me just briefly say how the Dandegram in fact produce. So let's see, we have we have the whole observations a big circle. So then I will start. So with the 4 is the biggest circle, right? So I will start with going through this circle, the small circle of 2. Then I do have P4 and P5 here. They are close to each other. Then for the third circle, I do have here, I will have some observations like P3 that is far from the observation of P1 and P2. So I do have P3, and then for the circle number 1, I do have P1 and P2. So this is the way that Dandegram in fact can be produced in a very simple way. And then by looking at this, we can see that there is 2 clusters here. And within each cluster, we have subclusters. So we don't, in fact, worry about subclusters. Mostly we started with these 2 clusters, and we produced the MSE to see if the 2 clusters are sufficient for this data or not. So, so that's one way to obtain the optimal number of clusters. So, and here I mentioned a few distances like Euclidean distances, Manhattan distances, weighted Euclidean distances that in fact work for different kinds of clustering. And so essentially are use Euclidean distances, but some people generate this distances to see if there is a different, differences between the number of clusters. So as I mentioned, because they are data-driven methods, that's why we should go through, just examining by observations to see how they looks like. So now I have already given you our examples. Now we turn to the principal component analysis. Let me look at my time to see how much I do. Okay, so for principal component analysis, how we can use it and why we use it. So essentially, so in clustering, what we discussed is we said that clustering is one way to summarize the complex real valued data point with a single categorical variable. So we want to produce, some categorical variable, and we want to have some labels for the clusters. So maybe, as I mentioned, for gene expression data, we can have malignant tumors, we can have benign tumors. So now, another way to look at when we have, like high dimensional data, or we have a quite large number of variables, is to use dimensionality reduction methods. So this dimension reduction will have 2 nice, in fact, properties. One is it is a way that we can use, regression analysis, because what we said that in regression analysis we need to have independent observations and correlated observations. Correlated predictors or correlated variables is always painful linear regression analysis. So when we do, in fact, principal component analysis, in this way, we can, instead of having, several hundreds of variables, we can have, for example, a few principal components that that have the most of the informations on those variables. So essentially, this is a way to simplifies complex high dimensional data, and also summarize the data with a lower dimensional real vector variables. So for any given d-dimensional data, we want to convert them into R less than D dimensions with minimal loss of information. So this is very important. So if we have, for example, 10,000 variables, we want to in fact to give to have, a few maybe dimensions, maybe 5, maybe 10, with the minimal loss of informations. So this is quite interesting. Then with this component, with this principal component, a few component, we can have any inference for our data set. So now let's see that for how it works. So let's see that we have two-dimensional, in fact, data. So we have x1 and x2. So looking at this, in fact, this picture, we say this is 2-dimensional. But now, what happens if I in fact produce a line like this here? So then the 2 dimensions will go through only y dimensions, right? So I can have, a linear combination of x1 and x2, and then I can produce this picture. And then simply the 2 dimensions will go through the y dimensions. So it tells me that I can use a linear function of my predictors, so that I can reduce the number of, in fact, predictors to a few components. So for example, this is another data. I do have like a 2-dimension data. So if we look at this 2-dimensional data in different ways or in different angles, what I see is the variability in this around this line around this line is too much higher than so much higher than the variability around this orthogonal line. So, or what I see is most of my variability is around, around this line. So it tells me that this is the first component, the first principal component that includes most of the variability in this data. And if I have this dimension as well, the second dimension as, this line as well, then I can add some, more variability, in the direction of this line, but that will not be so much important. So this line is my first principal component, and this is the second principal component. So what also I see is that these two components are orthogonal to each other. So this is nice thing because they will be independent of each other. So now I can, in fact, I can reduce my 2 dimension to again to another 2 dimension, but the first principal component is so much important because it includes most of the variability in my data. That's why I use first principal component, which is so much important than the second principal component. And we will see in the real example that it will include most of the variability in the data. So, and we will have, some, in fact, methods to see how many components we should have in our data. So, the way that principal component analysis works is that we project our X into Y. So based on this transformation, which is quite simple. This is like a very simple mathematics. And by this, our X's will become firstly independent. Will turn to Y. Those Y will be independent. And then a few of those Y, maybe Y1 and Y2 and Y3 can include most of the variability or most of the information in the data. So this is the simplest way that principal component analysis will work. Now, it has been used for many, in fact, purposes. For example, image recognitions. So let's look at, so if we want to have, lots of images and we want to extract the data from those, and then we want to use, classification based on those a few principal component analysis, then we would have these results. So for example, the first pictures of this guy is generated by only one principal component, which seems that it has nothing to do. It is quite, worse. So, but if we use only 10% of the principal components, then we can produce the second picture. And if I can use only 50% of the principal component, then I can have, the third picture that is quite, similar to the original picture that I do have here. So it shows that how we can use a few dimensions or a few variables to predict even the outcome variables, even to predict an image. And the second image is also has similar patterns. So if I use only one principal component, I will have only nothing. The second one is use only 10% of the principal component, which is good, but not so much. If we use 50% of the principal components, then we can have a nice, in fact, picture very close to the original pictures. So this is the way that principal components work. So essentially, we reduce the dimensions from, from many to a few, maybe, 10% or 50%. Then we can have the, in fact, it's kind of, removing the noise from our data. So let's go to a real R example and see how it works. So I am going to introduce, I will use the principal component analysis to prediction, and then you will be surprised to see how the predictions will work with this principal component. So I use my iris data again. So we had a structure of my data. So this data is quite known for us. So since I will use the prediction based on the principal component analysis, that's why I use training and testing, because I want to test in fact the accuracy of principal components in the testing in the testing method. So here is the pair panels for my observations. So note that one important thing here is that for for those things that we covered today so far, and also we will cover maybe for factor analysis. So we need something that is quite essential for our data is collinearity. So some people was thinking that collinearity is quite, you know, is not good, but however, for PCA, for random, I mean, for PCA, for clustering, and also for, in fact, for factor analysis, we need to have correlated observations, because if the observations are uncorrelated, then the principal component analysis will not work. But if the number of predictors are, you know, are so much, then you know, having high correlation is inevitable. So I mean, we would have, you know, highly correlated observations when we have large number of predictors, essentially in the medical science. So so whenever we have correlations, then we can use principal component analysis to reduce the number of variables. So I did so principal component analysis by this function, PRComp function. So in the training data, so, and what I see is my principal components. So I do have 4 principal components. And so the first principal component have the standard deviation of 1.71. The second principal component has the standard deviation of 94.94, etc. Now, the proportion of the variance can be explained by this principal component, is that the first principal component can explain 73% of the variability in the data. It means that I can get 73% of the information in this data only by having one principal component. So, and if we look at the cumulative proportions, it would tell us that I can get 95% of the information with only 2 principal components. So, which is quite good. Then we can remove in fact, the rest of the observation, I mean, the principal components, because the rest of the principal components or the rest of the variables can only, you know, produce only 4% of the variability or informations. So I will use these 2 principal components for prediction, and then you will see how much prediction accuracy. So the number of principal components should be in such a way that we can have, you know, more than 75% of the variability. Or even like for in these cases, only, you know, one principal component is somehow enough, you know, because 73% of the variability is not so much bad. But to me, I would use 2 principal components to catch most of the informations. So we can have, you know, the PC centers, we can have the scales, and we can have my principal components, and I can also have, you know, I can also have the relation between the principal components and the variables as well. So what I see is that the first principal component is correlated with sepal lengths, with petal lengths and petal widths. So I have combined these 3 variables into only one principal component. And the second component, what we see is that it is correlated with the sepal widths. So it tells us one thing, that we have 2 clusters in these observations. So we had clustering for these observations, and we mentioned that we should use 2 clusters. And exactly we see here that in fact the 2 kind of principal components here. So the first principal component is correlated with the sepal lengths, petal lengths, and petal widths, and the second principal component is correlated with this variable. So it should so we can summarize our data in these 2 principal components. And so let me skip them, and then so what we mentioned is that our principal components are orthogonal to each other. And in fact, we see here that so there is no correlation between the PCAs. So this is the distribution of the first principal component, this is the distribution of second principal component, this is the distribution of third and fourth principal component. So, and what we see here, these zeros are the correlations. So we have zero correlations between the principal components or between these four new variables, which is quite interesting because we don't need to worry about the collinearity that Alireza was telling about, high inflation rate, or producing bias, how high bias for our estimates, etc. We can use these four principal components to make our job easy. So now, we mentioned that we are going to do some predictions based on these principal components, and I want to use my predictions to see how much the misclassification error for this data. So I used a multinomial regression analysis. So here my model is multinomial regression because I had three kinds of species, Setosa, versicolor, and virginica, and I put them in front of PC1 plus PC2. So what I see here is that if I use only two principal components, then my misclassification error rate will be only 6%. So, and now let's see what will happen if I use only one PCAs, how much the classification accuracy will be. So let's run the code and see. So even with one classification, what we see is that the misclassification error is almost same. So in the past we had 6%, so misclassification error, and now I do have only 5% of misclassification error. So and we see that all Setosa in fact correctly predicted. Virginica, versicolor, so we had 40 virginica, 4 of them incorrectly misclassified and 36 correctly misclassified. So for virginica we have 3 misclassification. So but overall misclassification error is 5%. So which in fact is not so much bad. So with only using one variable or one in fact principal component, and this is in fact in training data. Let's see what's happening in the testing data. So in testing data, as we know that the testing data is independent data, so my classification error will increase a little bit to 13%. So if I use only one principal component instead of using 4 correlated variables, then I will have 13% of misclassification error, or maybe 87% of the accuracy for my data. And it shows that how can I extract the 2 PCAs or 1 PCAs from this data, and then how can I use them to prediction and to interpretations. So this is the way that I conclude the principal component analysis. Now, if I do have time, I can introduce factor analysis. If not, then we can stop here. So let me look at my time. So we had until 4:35. So Dr. Saleha, do I have time?
Dr. Reza, this is extremely valuable, all that you're doing. Now, how much time would you need for the factor analysis?
So maybe I can introduce, a little of what factor analysis is, and then I can simply run a code. 10 minutes is enough at most. Five to.
Is it possible to do it in 5 minutes, please?
Yeah, okay. I'll try my best to do that.
Thank you very much. Thank you.
No problem. Thank you. So let's go to factor analysis to see what's the factor analysis. We cover principal component analysis. So in factor analysis, that is in fact a statistical method used to describe the variability among observed correlated variable in terms of potentially lower number of unobserved variable called factors. So what we say is that our observations are related to some unobserved variables or called factors. So for example, math grade, physics grade, or even language grade, maybe somehow indicator is like maybe influenced by being a smartness or intellectual. So that's why we want to see which latent variables or which unobservable variables in fact produce these observations. So factor analysis search for such joint variation in response to unobserved or latent variables. So for example, let's say we have some, some questionnaire, A1 to A5, C1 to C5, E1 to E5, and N1 to N4, and O1 to O5. So these four observations, in fact, these four variables, maybe they can be influenced by something called agreeableness. So the second observations or variables can be, influenced by, consciousness, and these observations may be influenced by something called, extroversions. So these are the factors that, in fact, they are unknown, but in fact they have influenced, our observations. So essentially, we want to see how many factors that influenced our, in fact, observations. Somehow, I mean, these factors, in fact, are unseen or unobserved, and we statisticians always work with maybe with psychologists, with other scientists, to find out, what is the common things between these, these five observations here, and then they can label them as maybe, agreeableness of people, or consciousness, or etc., or whatever. So this is the way that we can explain, factor analysis. So there is a difference between factor analysis and principal component analysis. So in factor analysis, our factors, in fact, influence our variables. So there is a factor here that can influence variable 1, 2, 3 to be generated, but principal component analysis works in different ways. So we have, we have some variables that can produce, a component. So this is the way that these two are different. So in PCA, in principal component analysis, we want to have a linear linear combination of the variables that can produce a unique variables that mostly, includes the variability in the data. But factor analysis goes in different ways. One factor, produce some variables. So, and we want to see what is that factor and how it works. So, and one more thing that, in fact, beyond the factor analysis, we can have something called structural equation modeling, that we want to see what is the factors, how the factors are in fact correlated to each other, and how we can identify, a general model that in fact produce the variability in our data, or can model, our data. So this is called something structural equation modeling, almost a new science, and they are attract many people, both in applied and in pure statistics. So let's do quickly a factor analysis here. So let's look at the state. So for factor analysis, I need to have these libraries, ggplot, core-plot, GP annotations, and n factors. So I do have 6 variables that I know how I generate them. Variable one and variable 2 are two variables that are close to each other. In fact, variable 2 is in fact a noise plus variable 1. Variable 4 is noise plus variable 3. Variable 6 is noise plus variable 5. I mean, variable 5 and 6 are correlated, 1 and 2 are correlated, 3 and 4 are correlated, and I will show you how they are correlated with this plot. So so we see how the correlation between the variables, and we want to see how many factors in this observations. So in order to do a factor analysis, we just need to use factanal function for my data, and then I will introduce how many factors I want to have. So I use the 3 factors. So if I use 2 factors, then let's see what will happen. So if I use 2 factors, then it will show us how my factors are. So factor 1 is associated with the first variable, and second variable also the other variables, which in fact is not true, because we know that factor 1 should only associate with 2 of the variables. So it means that the model has not been well established. And also the test statistics here will tell us that 2 factors are not enough for these observations because the p-value is less than 5%. So, but if I use I use 3 factors, and so then I would have, let's see here, very nice thing. So the first factor is associated with the variable number 5 and variable number 6. The second factor is associated with variable number 2 and number 1. And the third factor is associated with number 3 and number 4, which in fact now we can have a common name for them based on the the other expert people. So I have used the factor analysis for another data set, for food data set here. And let's see so this data set is available, freely available in the internet. So so if we use factor analysis to see what influenced the structure of the variables, to find out what are the variables or what are the common factors behind those, then we can have like these interpretations. So factor 1 is associated with the oil density and crepsy of the products. And the second factor is associated with the fracture and hardness of the variables. So we can have a common name for these 2 factors. And this is not something that a statistician can do. This is something that in fact is those related science should see, that what is these 2 factors in fact associated with these variables. And so maybe they can have some interpretation for this data and so on. So in fact, for producing factor analysis, we need something called Varimax rotation to look at the data in different angles to have better interpretation for our factors. So, okay, thank you very much. So I don't want to take more time, as I think my time has been passed. So
thank you so much, Dr. Reza. You can also maybe repeat a little bit of it that we're now having with you and Alireza in the next one, which is the 7th of February 2021, inshallah. So
yeah, inshallah.
If you feel that
because I have one question.
Okay,
no, not yet, my dear. Inshallah, in the next, because I have few questions regarding that. Very quickly, this is the factor 1 and factor you have shown over here in the screen is the oil and density. So these are the correlation values, is it? So factor 1 is correlated like with this. What is this?
No, these are not. These are not correlations. These are something we call as loadings. So
yes, loadings. Okay.
Not the correlations. Or these are some.
So what would be the appropriate value, you can say? Anyhow, I will jot on my questions and ask to you in the next workshop. I think it's better. Thank you very much, Dr. Sam.
Thank you.
Thank you very much.
All right, Dr. Reza, I will now share my screen and we will be going towards the closing of this workshop. I'm going to share my screen now, ladies and gentlemen. Can you see my screen now?
Not yet. So let me unshare. Let me see.
Yes,
how
please.
I can do it shows it is shared, but I don't know why it doesn't show the unshared icon here.
It would just say, I think it would say hide or something.
You can make a shortcut Alt S. Alt S.
Alt S?
Yes.
Okay, thank you. Okay, thank you. Done.
So can everybody see my screen now? Hello?
Yes, yes.
Okay, all right. So the Q&A session would probably have to be next time because it's almost 5 o'clock. But of course, we must have a formal vote of thanks, which has been prepared by Ms. Kamal Aslam. However, I'm now having the problem that sometimes I have when I'm teaching my students also, that in this slide share mode, it is not, it's stuck now, it's not working. So Kamal, if you could open your own, could you do that, or should I try again without the slide share? Kamal, are you here? Miss Kamal Aslam, she was here, but I think her connection. Okay, she's back. Kamal, can you now look at my screen and you can read from here, maybe? Kamal, can you respond to me, please? I don't hear you.
I think there is some issue with Kamal system.
I think there is some problem. Okay. Let me then read what she had written. So she wants to say that it gives her immense pleasure to deliver the vote of thanks for this workshop. And she then proceeded to say that she would like to congratulate the PISTAR team and all participants for the successful completion of the third workshop on machine learning. This was her own, this all came from her side. And she wanted to thank profusely our invited guest, Associate Professor Dr. Aisha Bilgin, for the keynote speech on machine learning application for health problems. She wanted to express her special gratitude to lead resource person, Dr. Reza, and the co-resource person, Dr. Alireza, for their contributions to these series of workshops on machine learning. And she has written that it is always a pleasure to work with such hardworking and engaging people. She wants to pay her best regards to all of you and also to the PISTAR team for their endless efforts and making every event successful. Well, this is from Kamal Aslam, but you see, she herself is a part of the team. And the second last slide here, or well, almost, is from my side, in which I would like you all to know that all of these people are members of my team. Mr. Muhammad Iftikhar, Executive Secretary, ISOS, Professor Muhammad Aslam, Professor retired FC College, Dr. Sharka Hashmi, Assistant Professor, Lahore College for Women University, Ms. Saleha Mashkoor, Lecturer at Minhaj University, and Ms. Kamal Aslam, who has been my own student, and also Ms. Aqsa Abid, who has completed a BSc honors in statistics from Convener College and spent, honestly, ladies and gentlemen, without any exaggeration, hours upon hours with me on, preparing different things. The focal person for this workshop is none other than our dear Dr. Syed Wasim Abbas. You, all of you know, because he's the one who's communicating with you and sending you these beautiful certificates and all the important material. And he is Assistant Director at the Bureau of Statistics, Punjab. Thank you so much, Dr. Wasim, for doing so much for this PISTAR International Training Program. And I'm the convener of this program and honorary director. So, ladies and gentlemen, see you again, inshallah, on the 7th of February, 2021. Prior to asking you to, begging leave and asking you to do other things now, I would like to stop sharing my screen, if I can do that now, and request people to open their cameras so that we can have a group photograph. So all those who are comfortable doing so, it would be very kind. And my own team members, please, everybody, open your cameras so that we can have. So Attila is also here. Thank you, Attila. Thank you so much for joining.
Thank you.
Dr. Attila Goftas from Turkey, who has been our invited speaker. Okay, half of us have already opened our cameras, but the other people are, I suppose, a bit shy. There's still some chance of getting yourself photographed, ladies and gentlemen. So please, rather than being shy, I think you should open your cameras. Okay, thank you very much. The name comes as Daniel Roberts, but I would like you to give me your actual name, please.
Yes, it's Danielle.
Danielle, okay, okay.
From
Thank
South
you very
Africa.
much. From South Africa, sure. Okay, ladies and gentlemen, I hope Kamal and Aksa have taken screenshots, and so that the beautiful these videos of screenshots that Kamal prepares, this one can also be a part of it. All right, thank you very much. Ladies and gentlemen, it is time to say goodbye now. So inshallah, we'll meet again. Goodbye and Allah Hafiz.